Hello learners, I am Dr. R.B. Malati, Assistant Professor, Chhattisgarh Swami Vivekananda Technical University, Bhilai. I welcome you all again to the course Essentials of Surveying, Application and Techniques. We were discussing on photogrammetry. Since its inception, photography has gone from balloons and kites to airplanes, satellites and now unmanned aircraft system UAS. Interesting field to explore on. With this note, let us see the outline of last class module. So, in the last module, we spoke about terrestrial photogrammetry. We understood the definition of photogrammetry, the difference between photograph and image. We explored the history of photogrammetry, tracing its development from the Renaissance to the advanced digital methods used in the present day. Additionally, we also learned how to calculate the scale of the terrestrial photographs and determine their focal length. Let me take the class forward. Today, we are going to speak about vertical photogrammetry, that is aerial photogrammetry. Imagine you are tasked with mapping a vast forest or a large city. Instead of exploring every corner on foot, you would deploy a drone or a plane equipped with specialized camera to capture high resolution images from above. This is aerial photogrammetry. So, in simple terms, it is a technique that allows us to create detailed maps and conduct precise analysis using the photographs taken from the sky. Therefore, how should be the camera? The cameras used are sophisticated instruments with fast lenses, high speed shutters designed to capture sharp, detailed images quickly as they fly over the area, isn't it? Hence, camera and the orientation of the camera axis is very important. So, this aerial photographs are classified based on the orientation of the camera axis. True vertical photographs, second one near vertical photographs and the third oblique photographs. We will not go into for further bifurcation, but we will try to understand the small nitty-gritties of these aspects today. First, true vertical photographs. These aim for a perfectly vertical alignment, much like a plumb line passing through the exposure center. Plumb line meaning the line that you have seen when suspending the plumb bob. That is a line which is directed to the center of gravity of the earth. While they are ideal for precise mapping, true vertical photos are rare in practice due to the challenges in maintaining the perfect alignment. So, near vertical photographs, that is our second option. And these are almost vertical with a slight tilt controlled by gyroscopic mounts, ensuring the tilt is minimal, typically less than 2 to 3 degrees. These photos are used for most mapping application because they offer a good balance between coverage and accuracy. The third one, oblique photographs. These are intentionally tilted. In this, the low oblique photo don't show the horizon and are useful for detailed area studies, whereas the high oblique photos include the horizon. Meaning of horizon, the line at which the earth's surface and the sky appear to meet. These oblique photographs cover much larger areas. For example, during a natural disaster, high oblique photos can help emergency responders to understand the full extent of the affected area very quickly. And one more thing that we have to remember here is, if these images are used for such precise analysis, a process called orthorectification is applied. This technique removes geometric distortion from tilted photographs, transforming them into accurate top-down views. These days, this geospatial technology opens up numerous career opportunities and applications, from environmental monitoring and urban planning to archaeology and disaster management. Recently, even I noticed that Department of Science and Technology, shortly called DST, has also floated calls for proposal on the same. Absolutely, the choice is yours. Let us now look into the geometric properties of aerial photographs, focusing specifically on frame photography, which captures images in an instant. Imagine you are using a drone to take aerial photos of your own college campus again. So, understanding the geometric properties of these images is quite important for accurate mapping and analysis, isn't it? I would like to put forth the same sentence that I did in the last lecture. These definitions can be found in any surveying book available in your college library, but you have to take an effort to pick a book from the library absolutely at your free time. Let us start with the principal point, that is the first one. I request you to kindly look the figure right in front of you for easy understanding. Principal point. Principal point is a point where a perpendicular line dropped right from the nodal point, that is O, strikes a photograph. This can also be said that the principal point is a point where the camera's optical axis intersects the image plane. In the figure on the screen, small k is a principal point, and the point capital K is known as the ground principal point, where the line capital OK produced meet the ground. Next is the nadir point. Nadir point is a point where a plumb line, that is a line directed to the center of gravity of the earth, which is vertical line, dropped from the nodal point pierces the photograph. Thus, in the figure, small n is a nadir point, which is a point vertically underneath the exposure station. This point is also known as photonadir or photoplumb point. Ground nadir point. Ground nadir point or ground plumb point is a datum intersection with a plumb line through the frontal nodal point. It is a point on the ground vertically beneath the exposure station, such as the point mentioned in capital N in the figure. Principal plane. A principal plane is a plane defined by the lens capital O, the ground nadir point capital N, and the principal point produces the ground capital K. It is thus a vertical plane with a small nk or capital NOK in the figure. Principal line. A principal line is the line of intersection of the principal plane with the plane of the photograph. It is thus the line on photograph obtained by joining the principal point K and the photonadir point small n, such as the line small n K is in the figure as a principal line. Swing angle, mentioned in small s, is the angle at the principal point measured from the plus of y axis clockwise to the nadir point. Azimuth is a horizontal angle measured along the ground nadir point from the ground survey north meridian to the principal plane of the photograph, such as angle theta in the figure is thus the ground survey direction of the tilt. Isocenter. The isocenter is a point on the photograph where the bisector of the angle of the tilt intersects the photograph. Thus, in the figure, small oi is the bisector and small I is the isocenter. The isocenter lies at a distance of f tan t by 2 from the principal point. Kindly look closely to the figure on the screen. Tilt angle. The angle of tilt, which is also simply called as tilt, is the angle between the camera's optical axis and the vertical direction, which is a plumb line, at the time a photograph is taken. The line I1, I2 in the figure is the axis of the tilt. As we can notice, as all the lines are perpendicular to the principal line, it is also known as isometric parallel. True horizontal line. Intersection of a horizontal plane through perspective center with photograph on its extension. In the figure, small h is a horizontal line. The horizontal line falls within the extent of the photograph only for high oblique photographs. So, the next one is the horizon point. The horizon point is where the principal line intersects the true horizon line. So, while doing this, we adjust the projection center to ensure the image closely matches the real world screen, enhancing the accuracy. Therefore, we can say understanding photo scale is the next important thing here for accurate mapping and analysis. Let us consider how it works with some examples. Photo scale in aerial photography is similar to the scale of the map, but with an important difference. Photo scale in aerial photography is similar to the scale of the map, but with important difference, I should say. In a map, the scale is uniform because it is an orthographic projection, meaning every part of the map is scaled equally. I will repeat, orthographic projection means oblique projection. This type of projection is to accurately represent the models. It ignores perspective. So, parallel lines remain parallel and there is no perception of depth. This makes it easier to work with and can be useful when making accurate measurements. However, in photograph, the scale can vary because it is a perspective projection. Here, what is perspective projection? Yes, that is a projection that simulates how the human eye sees the world, making it useful for creating a real life view of a scene. It shows distant objects are smaller and lines of projection is no longer remains parallel here. Imagine you are taking a photo of a hilly terrain. Areas at higher elevation appear larger in the photo because they are closer to the camera, while lower areas appear smaller, isn't it? With this background, let us first start with a flat terrain to undergo scaling process. Picture a drone flying at a constant height, taking a vertical photo of a flat field. The scale of this photo depends on the focal length of the camera and the height of the drone above the ground. For example, assume if the drone is flying 1800 meters above the sea level and the ground elevation is 300 meter and also the focal length of the camera is 152 mm, the scale can be calculated using the formula scale denoted by capital S is equal to small f by capital H minus small h. So, S is equal to 0.152, is given in the question, divided by capital H, that is 1800 minus small h, that is 300, which will give 1.0133 into 10 power minus 4, which can be written as 1N9868. This means every millimeter on the photo represent 9868 millimeter, that is nearly 10 meter on the ground. How beautiful! And now, let us move to the variable terrain. Imagine taking a photo of a mountainous region. I hope everybody loved that. The elevation varies significantly. So, the scale will change across the photograph. For example, if points A, B and C in your photo are at elevation 1500 meters, 1200 meters and 1000 meters respectively, and your drone is flying at 3000 meter above the sea level, we can calculate the average scale. First, let us find the average elevation of this. S average is equal to small f by capital H minus small h average. Here small h is replaced by h average now. Hope you are noticing it. So, average elevation is equal to 1/3 of 1500 plus 1200 plus 1000 is equal to 1233.22 meter. Therefore, S average is equal to 0.150 divided by 3000 minus 1233.22, which is equal to 8.491 into 10 power minus 5, or simply can be written as 1 in 11778. So, every millimeter on this photo represent approximately 11778 millimeter, which is nearly 11.8 meter on the ground. Very interesting. And understanding these concepts is important when creating an accurate map for aerial photos. For instance, when city planners design new infrastructures, they rely on these scales to ensure accurate placement of roads and buildings. Similarly, environmental scientists use these scales to track changes in landscapes over time, such as deforestation or glacial retreat. Okay, having understood the scale, let us learn how to determine the ground coordinates of point and calculate the distance between them using photos. Imagine you are mapping out a landscape from high above and need to convert these photos into accurate measurements on the ground. I will repeat, imagine you are going to map out a landscape from high above and need to convert these photos into accurate measurements on the ground. If you are looking at the photograph taken from the aircraft flying at a certain height above the ground, and you need to translate the photo coordinates into the real world coordinate. That is what you are going to do. Here, when you talk about the ground coordinates, it means you are referring to the position of points on the earth's surface, measured from coordinate system with capital X and capital Y axis. These ground coordinates can be determined by analyzing the small points on a photograph, where the photo coordinates are measured with respect to the small x and small y axis. How beautiful! Now, kindly see the figure closely. Let us say we have 2 points capital A and capital B on the ground that appear as points small a and b on the photograph. The coordinates of these points on the photo are xa, ya and xb, yb. And their ground coordinates are capital XA, capital YB, YA and capital XB and capital YB. The elevation of these points above the datum as reference level, usually sea level, are HA and HB respectively. Using the principle of similar triangles, as always, we can relate these coordinates to the following formulas. The ground coordinates of the point capital A and B are XA, YA, XB, YB. Let HA and HB the elevation of the point capital A and B above the datum. So, we can write from the similar triangle OK by OKA is equal to small xa by capital XA is equal to small ya by capital Ya equal to F by H minus HA. I will repeat, you need to see the figure closely. It is just applying the similar triangle. We can arrive at OK by OKA is equal to XA by capital XA is equal to YA by capital YA is equal to F by H minus HA. And also OK by OKB is equal to XB by capital XB is equal to YB by capital YB equal to F by H minus HB. Hence, as simple as that, we have capital XA is equal to H minus HA by F into XA and YA is equal to capital H minus HA by F into YA. Capital XB is equal to capital H minus HB by F into XB and YB is equal to capital H minus HB by F into YB. And in general, the coordinates x and y of any point at any elevation are xa is equal to 1 by sa into small xa and ya is equal to 1 by xa into ya, can simply be written, isn't it? So, what does this say? So, every millimeter on the scale represent approximately x times a millimeter on the ground. So, if the ground coordinates of 2 points A and B are known, the horizontal length of the line AB can be determined using the formula L is equal to root of xa minus xb the whole square plus ya minus yb the whole square, where xa, xb and ya, yb are the ground coordinates of the point P, and the algebraic signs of it should be considered while substituting in the above equation. To make this even more easy and more practical, let us consider an example. Imagine a person standing in the second quadrant and his house is located in the fourth quadrant. We can determine the distance between where the person is standing, that is point B, and his house point A using the coordinates of these points. The formula of the distance L is L equal to root of xa plus xb the whole square plus ya plus yb the whole square. In another scenario, if the person is standing in the first quadrant and his house is in the fourth quadrant, we can use the same formula to arrive at L. So, capital L is equal to root of xb minus xa the whole square plus yb plus ya the whole square. It is very simple. We have just considered the algebraic sign. Understanding the location of points in their respective quadrant is important for accurate distance calculation, but it can be easily done as per the simple consideration that I just said now. The algebraic sum of it should be considered while substituting in the above equation. Let us look at an example to illustrate this. Example: the measured photo coordinates of image A and B of two ground points capital A and capital B are xa is equal to plus 45.35 mm, ya is equal to plus 38.41 mm, small xa is equal to minus 40.16 mm and yb is equal to minus 45.65 mm. Determine the ground coordinates of A and B and hence compute the horizontal distance of the line AB. The elevation of points A and B are 200 meter and 150 meter respectively above the datum, and the flying height is 1500 meter above the datum. Take f is equal to 152.4 mm. So, what we understand from the problem statement is the elevation of points A and B are 200 meter and 150 meter above the datum, and the flying height is 1500 meter. The focal length of the camera is 152.4 mm, and we need to determine the ground coordinates of A and B and then compute the horizontal length of the line AB. So, using the formula, that is capital Xa is equal to h minus Ha by f into small x, we can obtain the solution. Substituting those values, Xa is equal to 1500 minus 200 divided by 152.4 into plus 45.35 is equal to 386.84 meter. Done. We also know capital Ya is equal to capital H minus Ha by f into Ya. With that, substituting those values, we can obtain Ya is equal to 1500 minus 200 divided by 152.4 into 38.41 is equal to 327.64 meter. We can also calculate Xb is equal to capital H minus Hb by f into Xb. There, substituting those values, Xb is equal to 1500 minus 150 by 152.4 into minus of 40.16 is equal to minus 355.75 meter. Similarly, YB is equal to H minus HB by F into YB. YB is equal to 1500 minus 150 divided by 152.4 into minus of 45.65 is equal to minus 404.38 meter. Therefore, the L is equal to root of XA minus XB the whole square plus YA minus YB the whole square. Substituting all the found values, L is equal to root of 386.84 minus 355.75 the whole square plus 327.64 minus of 404.38 the whole square, which comes around to 1042.73 meter. Therefore, L is equal to 1042.73 meter, which is the answer. So, the horizontal length of the line AB is approximately coming to 1042.73 meter. This example shows how we can use photometric techniques to convert photo coordinates into real world measurement, which is incredibly useful for mapping and surveying. We will discuss only the concept of relief displacement in the aerial photography today, and worry not, the derivation will be explained in the next module. Moving to the relief displacement. In aerial photograph, the scale of the photograph varies from point to point because the photograph captures a perspective view, which also means that this phenomena causes each point on the photograph to be displaced from its true orthographic position. I will repeat, this means that the phenomena causes each point on the photograph to be displaced from its true orthographic position. This lateral shift happens because of the elevation, also called relief, of objects above or below a selected datum, and this displacement is called the relief displacement. Thus, relief displacement is a lateral displacement or shift in the photograph position of the image of an object due to its relief. What is relief? The relief is elevation of the object above or below a selected datum. If the relief is above datum, the relief displacement is outwards. On the other hand, if the object is below the datum, the relief displacement is inward. As the datum is generally taken at the lower level, the relief displacements are normally outward. You can visualize easily from the figure on the screen. I will stop here. So, there you have it. In this lecture, we explored essential topics in aerial surveying, focusing on the geometric properties of the aerial photographs and their application. Finally, we applied this concept in practical examples to compute the horizontal length between the 2 points using their photo coordinates and elevation. Yes, a glimpse of relief displacement is also given today. And in the next module, we will learn how to calculate the height of the object from relief displacement, photographic overlaps, methods to calculate required number of photographs, time interval between exposure, and many example problems associated with each topics. Thank you for your attention. Looking forward to seeing you in the next class. Happy learning.